So now we're going to begin talking about exponential functions. Exponential functions can be identified because they have their variable in the exponent. So it's in a power, right? So when we look at this, we're talking about some base b. And that base, we say it must be greater than 0, has to be positive, and it can't be equal to 1. It's very easy for us to know why we don't want that base to be equal to 1, because 1 to some variable power would be like saying 1 squared or 1 cubed, and you would just get 1 out every time. So it has to be a positive number, and it cannot equal 1 when we're dealing with these bases. So in order to understand them better, let's graph this exponential function. So f of x equals 2 to the x. And so I have some x values here. You can choose any values you want. We're just going to, plot some x's and y's to get a general idea of the shape. And the more points you have, the better understanding you have of the curve. So I'm going to start with my positive integer values and 0. So 2 to the 0 equals 1. So that means if I plug in 0, I get out 1. 2 to the first is 2. If I plug in 1, I get out 2. 2 squared is 4. Plug in 2, get out 4. And 2 cubed is 8. So when I plug in 3, I get out 8. And so one thing I want us to notice is as my x's are increasing by 1, 0, 1, 2, 3, that's not a very big gap. If you look at your y's, they're doubling each time. 1 to 2, I added 1. 2 to 4, I added 2. 4 to 8, I ended up adding 4. Right? So those are getting bigger at a faster rate. And even if I were to plug in 4, 2 to the 4th is 16. So if I plug in 4, I get out 16. Or 5, 2 to the 5th is 32. So you plug in 5, you get out 32. And you start to see those y values are increasing at a faster rate, and something we might describe as exponentially. So looking at negative exponents, remember a negative exponent is like taking it to the other side of the fraction, right? So it drops it down. So if you plug in negative 1, you get out 1/2. 2 to the negative 2, I end up getting 1 over 2 squared, which is 4. So negative 2, 1/4. 2 to the negative 3, I get 1 over 2 cubed, which is 1/8. So negative 3, 1 over 8. And I can choose any smaller number. I could even go so far as go negative 10. And what is 2 to the negative 10? Well, that's 1 over 2 to the 10th, which is 2 to the 10th is 1,024. So if I plug in negative 10, I get out 1 divided by 1,024, which is a very, very small number. So let's look at plotting some of these values here on my x and y axis. Okay, so negative 3, we go up 1/8. That's barely above the x-axis. Negative 2 up 1/4, still pretty low. Negative 1, we're up 1/2. So you can see we're going up just a little bit, but barely. At 0, we have 1, and then I'm going to plot the point over 1 up 2, over 2 up 4, and over 4 up 8. So you start to see this curve form. And as we noted, by the time we get over here to positive 5, my graph is going to be way up at 32, which I can't even draw on my paper within the scale I have established. So we see that it's starting to shoot up. And even in the other direction, if we came way over this way to maybe where -10 might occur, we are going to be at 1,024th. So, and you think about if you have one candy bar and you have to share that one regular size Snickers with 1,024 people, how much candy bar are you going to get? Hardly any, right? So it's getting really, really small. And my question to you is this value, as these y's get smaller, is it ever going to become negative? And the answer is no. It's always going to be a very small positive value. All right, so what that lets us suppose is that we have a horizontal asymptote here. We have this horizontal asymptote, this invisible boundary that we are approaching but can never touch at y = 0. Another notable point about this graph is we have a y-intercept at 0, 1. And so most exponential curves are going to have that same y-intercept and the same y = 0 horizontal asymptote. But as the bases change, in this case we had base 2, the curve is going to get, ever so slightly steeper or maybe change to a decreasing graph. Right now the graph rises from left to right, so it's increasing. So looking at what we have here, these are some properties of exponential functions. So what we're going to notice is that they are considered a continuous function, which is an important concept for when we get to calculus. They are one-to-one, and we talked about one-to-one in the last section. That means the inverse is also a function. The domain is all real numbers, but we have a range restriction. And so you'll notice that both of these graphs, everything is above 0, right? So it's 0 to positive infinity. And that's not to say that it's always going to be 0 to positive infinity, but we just have our most basic base raised to a variable power, an exponent. So we have two other pieces here. If the base is a value that is greater than 1, it can't equal 1, but if it is greater than 1, notice all of these graphs increase from left to right. So if the base is greater than 1, like 4, 2.5, or 1.8, we have a graph that is increasing. And that means it rises from left to right. Similarly, if we have a base that is fractional, and by fractional I mean between 0 and 1, like 1/2 or 2/3. Remember, 5/4 is bigger than 1. That is 1.2. So fractional is bigger than 1, not just any fraction, but bigger than 1. And if it is bigger than 1, our graph is going to be decreasing from left to right. It's going to fall. And you see that here, these bases 0.7, 7/10, 0.4, 2/5, 0.25 is 1/4. All of the graphs created here fall across the page from left to right. So we want to understand some of these characteristics, especially the increasing and decreasing. They always have a horizontal asymptote that is the x-axis, or y = 0, and a y-intercept. You notice they're all crossing at 0, 1. But does that mean that's always going to be the case? What if I had y = 2 to the x plus 10? So remembering everything we've learned about transformations, what does that plus 10 do to that graph? It's going to take that graph and cause it to shift up 10 units. And if it shifts up 10 units, then that asymptote and y-intercept would also shift up 10 units. Okay, so let's look at some transformations with exponential graphs now. So here we're given f of x equals 2 to the x is our parent function. And we want to describe the transformations that are occurring here. And if we can, let's list our new range and our new horizontal asymptote. So the first situation, 2 to the x minus 3 plus 4. So this is just like my graph of 2 to the x, but I have an extra minus 3 and a plus 4. So what does that minus 3 do? So remember, we talked about transformations in a previous chapter. If we apply that same logic, and in this case it was from our book, chapter 2.5, to an exponential graph, that might look like y equals a times some base raised to a cx minus h, and then we would say plus possibly a k value. Okay, so a multiplying by a shrinks, stretches, reflects vertically. Multiplying by c shrinks, stretches, reflects horizontally. Remember, horizontal does the opposite. Adding or subtracting h is going to shift something to the left or right, and the k is going to cause something to shift up and down. Remember, any of these values that are included with x, they're going to behave the opposite of the way they look. And what I always say is I think like they're in jail with bad x because they're naughty, and the ones on the outside are free because they know how to behave. So the ones on the inside do the opposite of what we are going to expect them to do. So in example A, we have this minus 3 and a plus 4. And what are those values going to do? So the 3, it's going to cause it to shift, and it's going to go right. We're going to shift right 3 units, and the plus 4 would cause us to shift up 4 units. So this graph that we have here would be shifted if we move it up 4 units. It would be up higher, and that horizontal asymptote would now be at y equals 4. So for example B, 5 times 2 to the x plus 1, we have a 5 and a plus 1. And what that 5 is going to cause to happen, it's going to stretch, it's multiplied on the outside, stretch vertically by a factor of 5. So it's going to get 5 times as tall. It's going to increase more rapidly. And then we are going to shift left 1 unit. And so in this case, because we are not moving the graph up or down, that horizontal asymptote is still going to be at y equals 0. And then, for example, C, we have 1/3, which is also negative, and a minus 7. So what that 1/3 does, it's going to shrink vertically by a factor of 1/3. The negative causes it to reflect across, and it's a vertical reflection, so that's going to go down across the x-axis. And then we're going to shift down 7 units. So because we are shifting down 7 units, that horizontal asymptote is now at y equals negative 7.